Hi students, in this video I would like to discuss about an important concept called resonance. So let us see what is the definition of resonance and what kind of molecules will go through the resonance. Okay, so I have given a definition of resonance up there. So look at here. So the delocalization of pi electrons in conjugated molecules or ions is known as resonance. So delocalization of pi electrons in conjugated molecules or in ions is known as resonance. Okay, so let us see what is meant by delocalization. So delocalization means movement of electrons. Movement of electrons. So what is meant by conjugated molecules or ions? So conjugated, the molecule is said to be conjugated molecule or the ion is said to be conjugated ion when pi bonds existed in alternative manner. Or pi bands and lone pairs existed in alternative manner. Okay, so let us see here one example. I have given, this is benzene molecule I have given. So look at benzene molecule. So in benzene molecule, there are three pi bonds are there and three pi bonds existed in alternative manner. So pi bond is there, again sigma bond, pi bond, again sigma bond, again pi bond. So pi bonds are existed in alternative manner. Therefore, benzene is called conjugated molecule. So in this kind of systems only you will be able to find resonance concept. What is mean by resonance? Delocalization of pi electrons. So what would happen? So delocalization means what? Movement of electrons, right? So movement of this pi electron will takes place. This pi electron will move there, and this pi electrons will move here, and this pi electron will move here. Okay, so consequently you will get one more resonance structure like this, and the double hand arrow represents symbol of resonance. Okay, so this is one resonance structure of benzene and this is the second one. So what is the purpose of resonance actually? Why that the delocalization of electrons should take place? If that resonance takes place, what would happen to the molecule? When resonance happens or delocalization of electrons happens, the molecule energy will go down. The molecule energy will go down. When energy of the molecule goes down, stability will increase because stability and energy will have inversely proportional relation. Okay. So as long as you increase the number of resonance structures, that much energy of the molecule will decrease. Okay. So accordingly, stability of the molecule will increase. That's the main purpose of resonance concept. Okay. Yes. Here the pi bonds are in conjugation. Okay. Sometimes pi bonds and lone pair of electrons also will be in conjugation. Let us take example of thiophene. Here the pi bond is there, sigma bond, pi bond is there, sigma bond. Here lone pair is there. Here lone pair behaves like a pi bond. Lone pair behaves like a pi bond. Okay. So this lone pair will participate in resonance. Resonance means delocalization of electrons. Delocalization means movement of electrons. That's it. When that movement happens, when you have alternative pi bonds or when you have alternative pi bonds and lone pair of electrons. Here sulfur is carrying a two lone pairs. One lone pair will involve in delocalization. So this will shift here and makes one pi bond. Consequently, this pi bond will shift here and becomes negative charge. As a result of this movement of electrons, you will get second resonance structure of thiophene. This is the second resonance structure of thiophene. Now again, what would happen? So now this negative charge, one negative charge equal to electrons. So one negative charge can make one pi bond. So now this negative charge makes pi bond and this pi bond becomes negative charge. Consequently, you will get this structure. Structure 3. Resonance structure 3. Okay. So again, what would happen? This negative charge can make one pi bond and this pi bond becomes a negative charge. Okay. So consequently, you will get this structure. Again, this negative charge becomes pi bond here and this pi bond becomes negative charge. Negative charge here. So finally, this is what the resonance structure will get. This is resonance structure 4. This is resonance structure 5. So for thiophene, you are getting 5 resonance structures. 5 resonance structures. So as long as you increase the number of resonance structures, stability also will be increased that much. Okay. So we explained what is meant by resonance. Okay, so what kind of molecules will undergo resonance? The molecules which is having alternative pi bonds, or the molecule which is having alternative pi bonds and lone pair of electrons can show resonance. Students, till now we have seen what is the definition of resonance and what kind of molecules or ions will show resonance concept. Okay, so now we are going to discuss about how to predict stability of resonance structures. See, some time back we have written resonance structures of different molecules. For benzene we have written resonance structures, and for thiophene also we have written resonance structures. But all resonance structures may not have same stability. If they are not having same stability, which is more stable and which is least stable? In order to find out the stability of resonance structures, there are a set of rules are given. Okay, so let us see one by one what are those rules. The first rule: resonance structure with more number of covalent bonds would be more stable. The resonance structure with more number of covalent bonds would be more stable. Simple example I have given here. So I have taken 1, 3 butadiene molecule, and this is the resonance structure of 1, 3 butadiene. So where this bond is polarizing this side, the pi bond is polarizing this side. Okay, this pi bond becomes a pi bond between these two center carbons. Since this carbon is losing pi bond, this will take a positive charge, and this carbon gaining pi bond, therefore this will take up negative charge. So this is the resonance structure 2, this is the resonance structure 1, which is having more number of bonds. Look at here. Here it has in addition to sigma bond, it has extra 2 pi bonds as there. In addition to sigma bond, it has only 1 pi bond. In which case you have more number of pi bonds or more number of sigma and pi bonds. Okay, here you have more number of sigma and pi bonds. Therefore, this is more stable, this is less stable. So the more stable resonance structure is this one. Understand? So let us go for second rule to find out stability of resonance structures. Okay, the structure which satisfies octet rule would be more stable. A structure which satisfies octet rule would be more stable. You guys mostly I think you know about octet rule. According to octet rule, when central atom surrounded by 8 electrons, that would be more stable. That would be more stable. Okay, octet. Oct means 8. When central atom is surrounded by 8 electrons, that molecule ion would be stabilized. So let us see, according to this rule, let us see stability of these two resonance structures. These two resonance structure. This is CH2 plus. So here the carbon is central atom, here oxygen is central atom, here carbon is again central atom. So look at here the carbon. This is one sigma bond with 2 hydrogens, 2 sigma bonds. So totally it makes 3 sigma bonds. Each sigma bond will take 2 electrons. So 3 sigma bonds means 6 electrons. So around this carbon you have 6 electrons. Therefore this carbon doesn't satisfy octet rule. Octet rule. So look at here. So this oxygen makes two sigma bonds, and two sigma bonds means 4 electrons, and two lone pairs. Two lone pairs means 4 electrons. So 4 electrons means 4 electrons, 8 electrons. Oxygen satisfies octet rule, but carbon doesn't satisfy octet rule. So let us look at this carbon. So this carbon is surrounded by 3 hydrogens. 3 hydrogens make 3 sigma bonds, right? 3 sigma bond, this side 1 sigma bond, 4 sigma bond. Each sigma bond will carry 2 electrons. So 4 into 2, 8 electrons. So this carbon will satisfy octet rule. This oxygen also satisfies octet rule. But this carbon doesn't satisfy. So this is resonance structure 1. Let us come here. When this lone pair involves in resonance, you will get this resonance structure. Here let us count number of electrons around central atom. Here also we have 3 central atoms, this carbon, oxygen, carbon. Look at here, this carbon is surrounded by 4 bonds with the 2 hydrogens. So with the 2 hydrogens, 2 sigma bond, this side 2 bonds. So this side 2 bonds, this side 2 bonds would be there. So total how many bonds around this carbon? 4 bonds. 4 bonds means 8 electrons. Therefore the carbon satisfies octet rule. According to octet rule, the central atom must be surrounded by 8 electrons. Got it? Yeah. So look at here. The oxygen is there. So this side 2 bonds, that side 2 bonds. That side single bond, this side 2 bonds. 3 bonds means 6 electrons. One lone pair is there. Total 8 electrons. Therefore, oxygen satisfies octet rule. Here, carbon. So same as here. This carbon also satisfies octet rule. Okay. So here all central atoms, this carbon, this oxygen, this carbon satisfied octet rule, whereas here this carbon doesn't satisfy octet rule. Since this is satisfying octet rule, all central atoms satisfying octet rule, this would be more stable. This would be more stable. So this is rule number 2. Rule number 2. Okay. So let us look at rule number 3. So rule number 3 would be given like this. The resonance structure would be more stable when negative charge is carried by highly electronegative atom. Okay. So let me write here. Resonance structure would be more stable if negative charge carried by highly electronegative atom. Highly electronegative atom. The resonance structure would be more stable if negative charge is carried by highly electronegative atom. So let me give two examples to predict the stability of resonance structures. Okay, so let me take CH2, no, CH3, CH minus, NO2. Yeah, this is one resonance structure I have given. Let us label this one as 1, and second resonance structure I would give like this: CH3 double bond, single bond, CH, where we have positive charge, double bond, N minus. Yeah. Yeah, look at here. I have given two resonance structures. This is the one, that is second one. So when this here, when this negative charge makes pi bond, this pi bond becomes negative charge. In this case, negative charge is carried by less electronegative element or atom, carbon. In this case, highly electronegative atom carried negative charge. So according to the rule, which one will be the more stable? The resonance structure which carries negative charge upon highly electronegative atom is more stable. Therefore, this is more stable. That is more stable. So this is rule number 3. So let's go for rule number 4. Rule number 4. See, we can see there are charges, positive charge, negative charge are present while you're writing resonance structures, right? So based on the charge distance, depending on the distance between positive charge and negative charge, we are also able to identify the stability of ions or stability of resonance structures. Okay, the resonance structure would be more stable when the distance between opposite charge and positive charge decreases. Stability will increase. Will increase. The stability will increase when opposite charges are close to each other. Or charges are close to each other. The stability of resonance structure will increase when opposite charges are close to each other. Let me take two resonance structures. So I have taken, this is a resonance structure of 1,3-butadiene. One more resonance structure also I can write. I would write like this. I will keep here pi bond and here positive charge, here negative charge. So this is resonance structure 1 of 1,3-butadiene. This is another resonance structure of 1,3-butadiene. Got it. Now In this case, opposite charges are far away from each other. In this case, opposite charges are very close to each other. Therefore, this is more stable. This is more stable. This is rule number 4. Rule number 4. Now, another rule we are going to discuss. That is the last one. Rule number 5. Resonance structure would be more stable. The resonance structure would be more stable when it contains more number of benzene rings. More number of benzene rings. More number of benzene rings. Okay. So let me take one example. I will take anthracene molecule. So I will write yeah. And another resonance structure of anthracene will be written like this. Yeah. So this is labeled as 1. This is labeled as 2. So both look same. The molecule name is anthracene. So anthracene, I have written only 2 resonance structures on the board. Among these 2, which is more stable. So what is the rule I have given there? So structure would be more stable when it contains more number of benzene rings. More number of benzene rings. Look at here. This is one benzene ring, right? Benzene means, within that one ring, you should have 3 pi bonds. So this is one benzene ring. Yeah, this is one benzene ring. But it doesn't look like a benzene. Pi bond. Here there is no pi bond. It doesn't look like a benzene exactly, right? It is also not looking like exactly pi. It is also not looking like exactly benzene. This is also not looking like benzene. This is also not looking like benzene. So it is it contains only one benzene ring. Look at here. Pi bond alternatively, we have alternatively pi bond. This looks one benzene ring. Here also this looks like one benzene ring, right? Pi bond gap, pi bond gap, pi bond. So it looks like a benzene. This also looks like benzene. So it contains 2 benzene ring. It contains only one benzene ring. Therefore, this is more stable. More stable. The resonance structure with more number of benzene rings will be more stable. Okay, this is also very very important point. So these are the 5 important rules to predict stability of different kinds of resonance structures. Okay, so these are very important for IIT JEE exams and NEET exams, because previously they have given many questions depending on the stability of resonance structures. Got it? Yeah. So now students, we have seen what is meant by resonance and what kind of molecules or ions now will show resonance structures, isn't it? We also now discussed how to find out or how to predict the stability of resonance structures. Okay, so based on the concept what we have understood, so I will give just few questions to make you to clear. Okay, so let me give question number 1. Just to try to write number of resonance structures for this molecule. So this is the anion I have given. So try to write number of resonance structures for these molecules. Okay, so previously I think 3-4 years back, this is the question they have given. So number of resonance structures are possible for this molecule. Okay, so try to write number of resonance structures for this molecule. Okay, so the answer is it is having 9 resonance structures. But try to present all resonance structures on the paper. If you have any doubt, just in the comment box you can send me message. I will try to reply back. Okay. Second question. So try to find out stability of following structures. Suppose I will give carbonate ion and I'll give SO2 SO3 2 minus ion, SO4 2 minus, and yeah, NO2 minus. So option A, carbonate ion, CO3 2 minus, sulfite ion, SO3 2 minus, sulfate, and nitrite. Okay, so four ions. So I have given four ions. So in four options, try to find out which ion would be more stable. The stability we have to explain depending on number of resonance structures. Depending on number of resonance structures, you have to find out stability. So already I discussed it, right? So higher number of resonance structures means higher would be the stability. So based on that point, easily you can find out which one would be more stable. Okay, so try to write number of resonance structures for this, and also try to find out, so among these four options, which is more stable. More stable, the one which is having more number of resonance structures will be more stable. Got it? So thank you for watching. Okay, if you have any doubts, try to reply back in the comment box. If it is on, if the video is useful for you, so like my video and share it to your friends. Okay, you can also subscribe my channel to get more videos about chemistry.